All right. So, yeah, so now we just start playing the junction rule / loop rule game. Okay? So let's find what's a loop that's easy to do.
The 9 and 50.
Yeah, the easiest loop is this one, wouldn't you say?
Yes.
Right? And then we go like this,
Yeah.
which means this has got to be like 9 volts, right? So when I say the voltage drop, I'm just going to say the voltage drop is 9 volts. Obviously, it means we're losing 9 volts. Everybody okay with that? Okay. So if that's 9 volts, then that's easy because Ohm's law says what? Yeah. And so we can say I is V over R. So 9 over 50 gives us 0.18 or something. How's everybody doing with that? Okay. Then the second obvious choice to me is maybe the long way around. Like this. That has to be 0 also. Okay? Now we know that the current this way is going to go in this direction. What will the current in that do? The current's going to come out of this. We know it goes here. That's 9 volts. That's 6 volts, so that's going to go this way. So it's going to go this way, through that, and that way. Oh, you know what? Let's do that loop first. Why not? Let's do the interesting loop. So that should go like this. Does that make sense to you? Because current comes out of the positive, and which battery is stronger?
9.
So does it make sense that the 9 would win over the 6?
Yes.
Okay. Now, this is where, remember what I told you about how things in reverse? Right? If this battery was this way, if it was in direction of the current, then it would add voltage. But because it's opposite, it goes the other way. Yeah, so this is going to be plus 9 volts, then this is going to lose some voltage. That's going to subtract voltage because you're going through the battery opposite direction, and then this one's left over.
Wait, so starting from that battery starts
Yeah.
subtracting?
Because like this, if you had, oops, that's green. If you had something like this, if you had something like that, you see both of these batteries are attempting to push current in the same direction. Does that make sense? So then if this was 9 volts and this was 6 volts, how would that be any different than this? Right? That's like the same thing. Because remember, you want to think of a battery as like a voltage escalator. I think your book actually has this analogy in it. Like where you get on the escalator at the bottom, and then the chemical process rises you up to the top, where you can like slide back down this whatever, or a ski lift, or however you want to think about it. You get what I mean? So if you do this, this one raises me up 9 volts, and then this one's going to raise me up 6 more. Does that make sense? Okay, but if I take this one and flip it this way, then that's like an escalator coming up on that side, right? Well, if this escalator is pushing people up to a higher level than this, then it's going to like fall, it's going to roll down that. But it takes away from their energy, if that makes sense. Right? Like you have a certain amount of energy coming from this. And then to push, if you're going to push it through this, it uses up some of that energy. Right? Okay. So, and the way we can write this out, if I did that in green, so we'll write it out something like, oh, sorry, we should have done this with the yellow. What we should have done was 9 volts minus, I guess we could say V50 equals 0. So that's what we should have put. Does that statement make sense to you? If it doesn't, please say so.
Is that for the bottom?
Oh,
Okay,
we're talking
Anthony,
about-
why did this is in yellow. This is for the yellow. Anthony, why did I write this statement out like that?
Because the remaining 9 volts that go from the first circulation has also goes to the second one.
Okay, so this is just for the yellow. This has nothing to do with the green circle, just the yellow. Does this statement relate to that yellow circle? Or whatever arrow? Why? How?
Because when it goes through the resistor, there's 0 amount of charge left.
Okay, and so everybody sees this yellow statement is an example of the what rule? Kirchhoff's? True, you really like Kirchhoff's.
Kirchhoff loop.
Yeah, okay, there you go. Loop rule. Yes? Does that make sense, everyone? Okay.
So V 50 equals V.
What's that?
So V 50 equals V.
Yeah, V equals 9. Yeah, so the voltage drop across V50 is 9 volts. So I just sort of did that in my head before, but I should have been discreet. Now, let's try it for the green. Actually, you know what? Do that. Try it for the green. Three volts, based on that statement, which Sam gave us, we should get 3 volts equals V30 plus V20. Okay? So, now, let's find another loop.
Big one.
Did you say the entire thing?
Yeah, so we can go the entire thing, and we know that the current's kind of going, I don't know, we can pick either way. I'm going to try this way.
Positive thing.
Yeah, now, it doesn't matter because it'll just flip the sign, the magnitudes will all be correct. So, yeah, go ahead, go, make this one, go.
The statement.
Make this statement.
Bye. It's a phone call.
Okay, here we go. Let's see.
The calculator.
Cindy, what'd you get? 6 volts. Plus V50 plus V20. Did anybody else get anything different? That's a horrible color for me to choose.
Yes. The red does not
I
contrast.
got
That's
plus 30 plus 50.
That's better. It's rose. Okay, so let's take a quick look. Anybody have anything different for that? Let's take a look. So what we're saying is just go around the circle and go that way. Okay, so then if that's the case, then the statements that we get are this V30, V20, V, all this stuff, and then we know V50, right? So then we get 6 volts equals V30 plus 9 volts plus V20.
We know, and we know that those two, V30 plus V20 equals to 30.
Okay.
Cause.
But there's a problem though, like, this is equal to 6. Unless the one we did was another way around, so that it would be 9V minus.
Okay, take a look at this. This is interesting. Let's use what Alvin just said. If I take this and plug this in, I get 6 volts equals 3 volts plus V50. Do you see there's a problem now? I'm going to get the wrong answer. So what does that tell me needs to be true about 6 volts?
It's not that.
This needs to be negative. Because what we have to be careful about the current. So then, right, because if I make this negative, and I put that over, then my V50 is minus 9 volts, which is what it really is. Right? I'm losing the volts across that. And what you have to do, what you see here, is this means, and what we know to be true, is that the current, I-50, flows that way. And if you go with it or against it or around it, right, like it changes how things go. And as you go this way, if you go with it and you're a resistor, that should have been minus 9 volts. So is this, if we put the negative 6 in here, does this come out to be the right thing? Yeah, totally, right?
This Isn't it be
because we subtract 3 volts, and that gives us V50 as negative 9.
Well, it's false out.
So, and got the 9 volts because of that one circuit
Mhm.
broke out.
Yeah. So I just substituted this in for this. So if we do this, well then this determines that should be, based on this circuit, it determines that should be negative. But then, I should already put it on that, okay. One thing, here, she's already kind of put it into a statement like this. What I recommend is that you kind of do something like this first. Just lay it out, see how these are minuses, and then you put it over here. That's why this is a positive 9, when we just calculated that V50 should be negative 9. Do you see what I'm saying? Cindy already moved this stuff over to the other side. Right? If she had left it the way it was, she would have said something like 6 volts minus V30 minus V20 minus V50 or something like that equals 0, right? But then she already put it over here, just to kind of let you know what we're doing there, what's going on. So yeah, that's fine. So then, if that's the case, knowing these things, what happens? We get negative 15 volts. Well, that's kind of annoying because that's,
V30 plus V.
how does that work?
Did you say it was a
Did you forget to
negative
change the
now?
signs?
So
Okay, so the way that Anna's suggesting is we have this R20 and R30 here. She's saying, well, why don't you just take this and do this so that the 9 volt and the 6 volt are going to cancel out. So you're going to get,
Now
let me do it on the bottom. You're going to get 3 volts here and then just one resistor, which is 50 ohms. Okay, and so then I is V over R, and then V that, so that becomes what, 0.06? All right? Yeah, 0.06 amps.
Oh, you're just putting this in series?
So that would be the answer of both.
Yeah, now let's see if Anne's smarter than I am.
And
What happens if you do V over R here? What do you get? Yay! I live to fight another day. 0.06 amps. Right? And same thing over here. 0.06 amps.
Yay!
Now it is very possible, it's very probable that Anne is smarter than I am. But at least in this sense, I didn't screw up.
Yay! Yay!
But yeah, so does everybody kind of see what I did and do you see what Anne did?
both come up to the same answer, right?
Yeah, they're both the same. So Anne's is like, well, duh, they're both resistors and they're in series, so why not just add them up? And then add the effects of the batteries, one being a negative effect, but you just add them, and then you do it this way. And then I was like, for some reason, my brain just did not see to connect these two resistors, so then I used a proportion of the voltage. And then from that, you get 0.06 amps here, and 0.06 amps here, for a total current out of this battery of 0.24 amps. Yeah. Yeah, that's just for that loop. Of the what? Yeah, the red loop should exist as well.
Is it needed?
Yeah, so if we do the, if we come from this battery and say +6, we have to look at the currents. Which way are the currents actually running? Do we see that the currents are actually running that way?
yeah, so
Right? Okay, this might confuse you a little bit, but this is all about convention and choosing your frame of reference. If we say that this battery is +6 volts, we have to look at all the currents, right? This is +6, but when we go through here, that's negative because we're going backward, or that's positive because we're going backwards through a resistor. If you go forward through a resistor, that's minus, right?
Because you're using.
Because you're using up voltage.
Because
But if you go backwards through a resistor, it's plus.
so it's
If
like,
you go,
so
go ahead.
it's like coming through this class and you're teaching the teacher.
Okay, sure, if that works for you, whatever, that's fine. But, so if I do it, it's like 6 volts, and then I'm gonna get minus V30, and I keep going around, but do you see now I'm going with this current? So then that's going to be plus, oh no, wait,
B50.
oh gosh, I just said that and then I screwed it up while I was saying it. Sorry. We were going backwards through this, so this should be plus V30, minus V50, and then we're going back up again backwards through that, so it's plus V20, and that should equal 0. And then look what happens. Like, this V50 is 9, right? So that means 6 volts and 9 gives me negative 3. That means V30 plus V20 is 3 volts, which we got in the very beginning. Ding.
So
So how do you do the actual math for the proportions to find for D30 and
Oh, technically, if you want to do the proportion math on that, you would say like this, something like, I know this is 20 ohms, I know, so I would be like R20 over
our total?
our total times V, I don't know, whatever, the sum of the voltages for that loop, which was 3 volts. So then that's going to equal V20. And then R30 over RT times the sum of the voltages for that loop is equal to V30. This is not a technique that you should, memorize. It's just logic, using logic. But does everybody get the red right here? This is the red. See, it always works out. As long as you stick with convention, like stick with what's really happening, it always works out.
So to explain, can you just really quickly explain that?
Go ahead.
The third, can you like because
Explain the which?
The red.
The red loop? Okay. So if I go from the red loop again, just remember I'm coming out of the battery, so I'm gonna have 6 volts.
Yeah.
Because, okay, basically this is kind of like, okay, the currents are determined. So the bell rings outside in the hall, kids are moving. The flow of the current in the hallway is what it is. If I go against that flow, I flip the effect. If I go with the flow, I add the effect.
Okay.
Okay, so I'm going to say that I'm going with the flow of the battery.
Yes.
So, because that makes sense. So that means I have plus 6. Now if I go through this resistor, which way is the flow? Against me.
Against.
So instead of subtracting V30, I should add V30, or whatever that is. Yeah, V30. Because we've already, well, just from looking at this, we should know based on the 9 and the 6.
Because the 9 will want to push current this way.
Does that make more sense? Does that make sense? It's almost as if you had two, like the escalators are like pumps. And one pump is pumping up to 9 feet, the other pump is pumping up to 6 feet. When you let the water go from the 9 feet, where's it going to go? Yeah, it's going to go down. So it's going to push water back through the 6th pump. So what's going to happen is the water, you can't beat gravity. So water is going to come down, but it's just going to be moving slower than if there was no 6-foot pump. You get what I'm saying?
So it's like almost like that one will release more.
Yes.
It will release more.
Yeah. Rather than quantity, because then it's going to make you start thinking the currents are a function of that. Think of energy. This pump puts more energy into the water. That's why I was saying 9 feet or 9 meters instead of 6 meters. So when that water cascades down, it's going to push
It
through.
takes more energy to go through the 9 volts than the.
So it's going to push down, and so it's going to split this way. And this water that's going here is going to go all the way back down. This ground is G. This is the ground. Right? So, I don't know, if you wanted to graphically depict this in your brain, it would be something like, okay. So let's say this is on the ground, and then there's this stairway up, right? And that is 9 meters. And then up here, the water is going to kind of cascade down like this. Then there, this isn't going to work. That's too weird to draw. I was trying to draw a 3-dimensional thing of this, but it's like too weird. Just think of these two are parallel staircases, but and they're both connected to the ground here. That's ground 0. And then this this staircase goes up higher than the 6-volt staircase. So when the water pours through this and travels out, it's going to go down this little chute, right? I don't know. Let's say it spins a wheel or something. So it loses some voltage. Then it's going to spill down this way, lose some more voltage, and spill down this last wheel, making that happen. Do you kind of see what I'm saying there? So this goes up really high. It goes up to here, and then it pours down a little bit, pours down a little bit, and pours down all the way back to the base. This one pumps it all the way up here, and then just pours straight back down to the base. I don't know, sorry. I don't know how to draw that to kind of show you what I mean. I guess if I draw the ground like this, something like that, that's the bottom of the staircase, and then this is R50, right? So this height right there is 9 meters. So you're looking at this like from the end, and then this is the 6-meter staircase, and then here the water falls down to here. Oh crap! This is the weirdest thing I've ever done. This is a 6-meter, and then it's going to pour like this, and this is R30, and that's R20. Okay, so here, imagine that you're looking at this from this perspective. Take this and lift it up. Like, look at it from this end. And this is what you see. Like a staircase, right, going up. So somebody, I don't know, is walking. Oops, that's a bad light. They're walking up that staircase. So the water is being pumped up there. The water or the people or whatever are being pumped up here. They have 9 volts. This pours down and loses 9 volts and is back to 0 volts at the bottom.
Oh.
Some of that water pours down here, and it's going to lose whatever V30 was, which was 0.06 times 30, so 1.8? Yeah.
1.8 volts.
This loses 1.8 volts, so it loses a little bit. Then this is trying to pump it like it's trying to pump against it. So instead of allowing that water to flow and gain the energy, it puts energy into it to reduce its speed. Does that make sense? So it's like, this is like a brakes. So this is a brake, the brakes of whatever pushing back through to not let it go. And then it loses its final 1.2 volts here.
Oh, so wait.
So this is minus, and that becomes plus.
So wait.
Oh, not plus. Sorry, minus. Yeah.
Because it's like at 9 volts, it has its full potential.
Yes.
And at R30, it loses a little bit.
Loses a little bit.
And then at 6 volt, and then when it gets to the 6 volt battery, it loses a lot.
Right. If you turn this around, then you would add the energy, and it would go faster as it goes downhill, right? Because you expect it to energy, but then because it's turned around, it slows it down, as if it was using up energy.
Because, well, it depends on the orientation of the battery.
Yeah, exactly. And then the final 1.2 volts is here. So you kind of get what the analogy is doing here? This is that circuit drawn out just like this.
Just flip it on its side. If it was going,
Like, that's this.
if the positive terminal on the 6 volt battery was flipped, it would, instead of going 9, it'll go lose 1.8 through the resistor.
And then it would be plus 6, boom, and it would lose like, whatever that is,
Whatever.
13.2.
So but it will still allow it to coast down.
Yeah, it'll just come down really fast right now. Okay? So, how we doing?
Interesting.
Loop rule? This is all using the loop rule.
You didn't even.
Alright, that was like a 30-minute problem, 40-minute problem.